Hello everyone, and welcome to the first unit of the series on density functional theory. In this first video in the series on DFT, I want to talk about the fundamentals underlying this theory to get to know the general concept behind. I will introduce you the fundamentals of DFT so that involves solving the many-body Schrödinger equation, and in the next videos I will go through more details and also move into DFT applied to crystalline solids about how to do our DFT calculations. So by listening to this unit, you will understand the fundamentals of DFT and it makes you ready to perform calculations which will be explained in the next units. So knowing the fundamentals is highly suggested to do more accurate calculations and feel better about the calculated results. Well, I would like to start to talk with this question that why is electronic structure important? And what we have been doing with wave function theory up to this point. Well, the wave function which we are deriving from electronic structure theory is useful because it contains really all the information about the system. Some of the information is useful, for instance, the electron density, that is the distribution of the electrons and the distribution of the electrons and the position of the ions give rise to certain important properties like dipole moment and more generally charge distribution. And the electronic energy, once we invoke the Born-Oppenheimer approximation that allows us to define potential energy surfaces. And with this energy surface, we can now talk about things like the energy of the geometries and the bond energies, barrier, Higgs equilibria between different minima and so forth. Now, let's talk about how to calculate the electronic structure. So let's take an example of a system and let's take silicon, for example, to get feeling about solving many-body Schrödinger equation. If we go through the calculation, we will find that there are two atoms in the silicon unit cells, which each atom has 14 electrons. So the silicon unit cell contains 28 electrons. Here you can see the silicon unit cell including only two atoms and calculated the band structure and the density of the state which is derived from the band structure. Well, based on wave function theory as first described by Erwin Schrödinger in 1925, all the information which is contained in the wave function can be determined from this antisymmetric function. If we swap the coordinates for all electrons, here we have 28 electrons, we would get a chance and sign wave functions. If we think of the spatial coordinates of each electrons, there are three directions of x and y and z. So there is 3 times 28, which is 84 coordinates. So it's an antisymmetric function of 84 spatial coordinates for the electrons, and the electrons also can have alpha or beta spin. And so there is 28 electron spin coordinates as well. So that's a function of altogether 112 different coordinates, that's a lot for a small structure contains only 2 atoms. Before going to the mathematics and physics behind the wave function theory and many-body Schrödinger equation that you can see a lot in quantum science without any explanation exactly what it means, which is fair, I think, because it's a very complex topic. I just wanted to explain what it actually means. So when you work on this topic, you can feel it in a better way. So the Schrödinger equation tells us everything we can possibly know about the quantum system. It's basically like a Newton's second law of motion, F equals ma of the quantum world. In the case of the throwing ball, we can predict its position and momentum for any moment in any time using the Newton's second law. Once we have these two parameters, we can derive basically everything else, such as velocity, energy, etc. But Newton's equations don't work anymore when we are working with atoms. We can't know both the exact position and the momentum of quantum objects, but we can know other things like the energy levels and the wave function. But that information is all inside this equation, the Schrödinger equation, that we need to extract them by some mathematics. So let's consider we have a very simple quantum system, like one electron in a box. We can't predict everything about this single electron using Schrödinger equation. For example, where the electron might be in the box and what energy level the electron might be at. In this equation, H is Hamiltonian operator, psi is wave function, and E is the energy level. So first let us start with psi, which is a wave function. Wave function tells us where the electron is probably to be in the system, but not where exactly the electron will be. So we can only predict where the electrons probably be in a system, not the exact positions. So we cannot tell where this electron exactly is in the system. Well, that's what the wave function gives us. The wave function tells us the probabilities of the positions of the electron in our system. Keep in mind that the electron is in a superposition of all possible places at the same time and not only in one place at a time. So what the wave function tells us is the probability distribution of the existence of the electrons in our system, like a wave, okay? So the probability of finding the electron at a given point in space, no, technically it's the probability density, but you can pretty much just think about this is the probability of finding the electron at a given point. So different kind of waves can represent different probabilities of where the electrons are most likely in our system. That's why the name is wave function. Well, it's a function that describes the wave shape of probability distribution of the electrons. Again, keep in mind that the electron is in a superposition of all possible places at the same time, and not only in one place at one time. Let's talk about E, energy of a system. It represents the energy the electrons are allowed to have in our system. As electrons move in the system, energies will change. Using DFT, we are seeking to find the lowest energy of the system, which is called the ground state energy. Now, before I explain what this term means, I just want to say that these values, E times psi, are the ones we are trying to solve. It's telling us that if we have the left-hand side of the equation, we can find out the energy levels of the wave functions of the electrons. And if we know these two terms, we can obtain everything else we can possibly know about the system, like the position and the momentum of the ball in our example that the Newton's second law was governed. Let's take a look to the left-hand side of the equation. Well, the total energy is made of kinetic energy and potential energy. So Hamiltonian operator is a summation of the kinetic energy and the potential energy of the electrons in our quantum system. We will talk about the Hamiltonian operator more in the rest of this unit. Let's briefly talk about many-body Schrödinger equation. Here is the Schrödinger equation, and I'm gonna talk about that very simple now. I will explain it in more details in the next videos, and because this video is just trying to introduce you only fundamentals. Many-body Schrödinger equation at a first glance seems to be very simple. H psi equals E psi. H is Hamiltonian operator, and it's not a scary word at all. E is the energy level of our system, and psi is the wave function. And all the information of our system is contained in the wave function. It means by solving this equation and obtaining the wave function, we can get lots of other information of the system and the ground state energy of a system. So if we actually expand the Hamiltonian operator, there's a kinetic energy term of ions and electrons. The first term is the kinetic energy of the ions, and the second term is the kinetic energy of the electrons. There is an interaction between electrons, and it's some integration over all space, the distance of the electrons in our system. So this term is for the interaction between the electrons in our system. This term is the one that's really quite tricky. That is the interelectronic interaction. There is an interaction between ions, and it's some integration over all the space distance also. And the last term is the interaction between the ions and the electrons in the system. So in general, the Hamiltonian can be summarized into different terms. A kinetic energy terms for the ions, the kinetic energy terms for the electrons, and this term is the electron-electron interaction in our systems, and the fourth term is the ion-ion interaction in our system, and the last term is the electron and ions interaction in the system. So let's talk about the challenges of solving many-body Schrödinger equation. Generic wave function psi is complicated. There are three coordinates. Well, we can, of course, consider four coordinates if we take a spin for every single electron. And there might be a lot of electrons in a complicated system. So electronic wave function lives in 3n-dimensional space. N is the number of electrons. So as the system grows, the problems begins to become quite challenging. The interpretation of bigger wave functions is much more complex than simple ones. We can of course operate on it with Hamiltonian operator and pull everything out, but if we look at the wave function, and as I said, it's an anti-symmetrized product of orbitals, and orbitals can be written as a linear combination of basis functions. It takes a computer to write down the columns and columns of numbers as a wave function. So it's of course not an easy interpretation, these columns of numbers. So as we have already explained, if we want to take silicon as an example with its 28 electrons in a diamond structure including only 2 atoms, the following Schrödinger's equation, Schrödinger's approach or equations, we would have a very complicated function. The diamond structure has 2 atoms in a unit cell. That means that we have 28 electrons, and there are 3 directions of x, y, and z. So there is 3 times 28, which is 84 coordinates. In order to understand the real challenge, let's say we would like to do simple integral over the wave function numerically by discretizing the space. Let's say in each dimension x, y, and z of each electron, we discretize the space only with 10 points. Just an example. If we want to do integration only in one dimension, we need to do 10 calculations in each of these points. If we want to do integration in 2 dimensions, our grid is 10 times 10, and we need to do 10 to power 2 calculations. In the case of silicon unit cell, the number of calculations we need to perform is 10 to power 84. That means that we have 3 times 28, which is 84 dimensional space. That's a big number for a simple system including only two atoms. Now let's see how big it is. The largest supercomputers today is going to do 10 over 18 floating points operation per second. It's a big number. If we want to do the calculation of 10 to power 84 using this supercomputer, we need 10 to 66 seconds. That's quite a long time. It's more understandable by taking into account that the age of the universe is 10 to 17. So it's clear that solving the many-body Schrödinger equation is impossible computational problem. So it was necessary to develop an approximate description that allows us to solve the Schrödinger equation in computationally meaningful way. So the question here is that how we can simplify this equation, for example, from three-dimensional space to three-dimensional space, and how can we escape from this three-dimensionality? As we already explained, the Schrödinger equation could not possibly be solved numerically because of dimensionality. But in 1964, Hohenberg and Kohn proposed density functional theory that we talk about that in more detail a bit later. And they propose that all the information in a system is contained in the electron density. So the electron density, of course, that is a very simple function of only three coordinates. So we live in three-dimensional space, so we can define the density at every position in a space as a function of only three coordinates. We'll discuss about DFT more later on this video. So both these two accomplishments by scientists in the 20th century was highly important, and each was awarded with the Nobel Prize. So Schrödinger published his work on wave function theory in 1925, and he was awarded the Nobel Prize in Physics in 1933. Hohenberg and Kohn published their works in 1964, but only Kohn was awarded the Nobel Prize, and not Hohenberg, because Kohn continued the theory, density functional theory, and did additional works, some of which we will see in the upcoming videos. Kohn shared the Nobel Prize with John Popple, who won it for practical wave function theory. Although Schrödinger developed the wave function theory, Popple made this theory more practical and kind of everyday tool. All in all, in 1998, Kohn and Popple shared the Nobel Prize in chemistry together. So let's talk about the calculation of Schrödinger equation, how to solve the Schrödinger equation in a very fundamental way, and we can discuss about that more deeply in the next videos. Generally, we have Schrödinger equation. H psi equals E psi, and we are going to find the ground state energy. To find the minimum energy, we need to find a wave function which minimizes the expectation value of the Hamiltonian over the wave function, and hence minimize the energy. So by having a trial wave function, we can start minimizing the expectation value, and as long as we find the wave function that in fact minimizes this expectation value, we have found the exact wave function, because from the variational principle, we know we can't go below the correct energy in density functional theory. Moreover, in DFT, there is a similar high-level approach that can be applied. So instead of having a wave function as our trial variable, we have a trial electron density in DFT. We are going to minimize an expectation value in the sense of an integral over all space and just put it in this bracket. to minimize the energy. It's the interaction of the density with the ions. So there are ion charges that are positive and they interact favorably with the electron density, and since the electron density is continuous through a space, we have to integrate over all space. And then what Hohenberg and Kohn showed was that there is some universal functional of the density that contains the rest of the energies that we would need, and that would include the kinetic energy and the electron-electron interaction. So by having that functional, we should be able to try density after density, and then we have tried all densities. The one that gives the lowest energy will be exact density for the system. So what's the problem now? Well, each of these theory has its own problem. So now let's come to density functional theory. So we are going to attempt to minimize this quantity by changing the electron density. But there is a small problem that we don't even have an equation for f, this universal function. So the Hohenberg-Kohn theorem, which is the heart of DFT, shows that this f, this universal function, which is the function of the electron density, exists, but it doesn't say anything about what this function looks like. So that makes it particularly difficult to solve the relevant equations. All in all, for this unit, as fundamentals of the density functional theory, we can say that the energy functional is divided into two parts. The first part is known part, and we know everything, we can calculate that in an exact way. And the second part is the unknown part, and which is called the exchange correlation function. By having this exchange correlation function, we can move from many-body Schrödinger equation that is computationally impossible to solve to many single electron Kohn-Sham equations that would be possible to solve. In density functional theory research, researchers try to develop this exchange correlation functional that will be useful in having a mapping with wave function theory. We will discuss about the density functional theory and exchange correlation function more in the next videos. In the next unit, we will continue talking about the density functional theory and discuss about the foundation theories and approximation behind the density functional theory. So please subscribe to this channel and hit the bell icon to be notified the next videos, and thank you very much for listening.